In this video, I want to talk about what happens when objects go in loops, loop-the-loops, or when they go over hills. You get the same sort of ideas happening, but the normal force in these problems is a little bit funky. All right, so here we go. Let's assume that I have like a roller coaster ride, and it starts out up here, and we have one hill like this, and then we have one circular loop. Then we'll just call them both. Both of these have a radius of r and a radius of r here, even though they might not look the same. All right, so in this problem, this roller coaster car will go up the hill, and then it will go around this loop-the-loop. Okay, so if I were to draw the free body diagram of the car at the top of the hill, this is not a weird idea, right? We have the force of gravity on this car and it pulls downward. As this car goes over the hill, though, there's also going to be a normal force of the surface of the hill on the cart. And so that's going to be an upward force. But because this car is moving in circular motion as it goes over the hill, the normal force is not going to be equal to the force of gravity, because we need a net force pointed towards the center of the circle so that this car can accelerate towards the center of the circle. So our normal force is going to be less than the force of gravity. Okay, now over here, this is a little bit weird. We still have the force of gravity on the car. It's still going downward. But you can imagine that the car goes around the hill, right? And so it's like me pushing up against the ceiling. In this case, the normal force is actually pointed downward. The force of the surface of my hand on my fist is a downwards force. So the normal force in this case will be a force that's pointed downward. The magnitude of that, again, is going to depend on how fast the car is going, because you can imagine as this car is going around the loop, the slower and slower it goes, the bigger and bigger chance it's going to be to fall off the track. So you can imagine a point where you have some minimum tangential velocity, VT min, where the normal force equals 0, and that's when the cart will fall off the track. Okay. Same idea with the hill. So as this car goes over the hill, it's not a minimum speed that we have to worry about. This car can go over the hill as slow as you want it. But you have to think of the maximum speed, the maximum tangential velocity, which with this car can go over the hill. Because if it goes really, really fast, it's going to launch itself. So the faster and faster it goes, the smaller and smaller the normal force gets. So at this tangential maximum velocity, the normal force will be equal to 0. Okay, so when you're talking about circular motion, we can say that the centripetal force is the sum of all of the forces in the radial direction, which is the mass times the centripetal acceleration. Okay. For both cases, surprisingly enough, if you're looking at this maximum value or minimum value, that's the case where the normal force is 0, and so you're left with just the force of gravity. I'm going to look at this situation. I'm just going to use this maximum speed as my example. So the faster and faster the car goes, the smaller and smaller the normal force gets. So even though the centripetal force is the force of gravity minus the normal force, because the normal force is pointed out of the circle and the force of gravity is pointed into the circle, we get force of gravity minus the normal force is mass times the centripetal acceleration. Remember, this is just the tangential velocity squared over the radius. In this case, this is going to be VT max, the maximum speed that the car can go over the hill. That maximum speed sends the normal force to 0, because we don't want it to be launched off the surface. All right, force of gravity is mass times gravitational field strength, m tangential velocity maximum squared over the radius. Our masses cancel, so that maximum tangential velocity, VT max, is going to be gravitational field strength times r square root. This should look familiar. In a previous video, we found this minimum velocity for a ball on a string, so the minimum velocity at the top of its motion. So at the top of a hill, the maximum velocity is going to be the same as the velocity as it's going over a loop or going around a loop. So this maximum speed is the same as this minimum speed. You can do the math. I think this is a really cool, interesting problem that is like mind-blowing. Where students have trouble with this idea of like loop the loops is like what's keeping the car on the road? Like why doesn't it just fall to the ground? And that's because the car is moving, right? So this car is moving around the circle, and so it wants to go in a straight line because that's the direction that it's traveling very fast in. And so the pressure, the forces that it feels from the track are bending it into the circle. And so that's why we sort of have circular motion here.